Well, hello, everyone. Welcome to MEERTALK. My name is Kathy Posey, your host for today. We're really glad to be getting together for another MEERTALK. Today, we will be hearing from Dr. George Tselioudis. Then we'll take questions from people in the MEER community. After that, we'll open it up for questions from all of you in our audience. In case you didn't see our recent newsletter, there are many updates, but I'll highlight just one, and that is that our India team kicked off a climate adaptation project in an underdeveloped neighborhood of Pune, just as early heat waves sweep across the country, unfortunately. In order to carry out all the projects such as this one in Pune, crucial for MEER's further development, we do rely on donations. If you don't already donate and you'd like to contribute toward our efforts to cool the planet, we appreciate your gifts. You can go to meer.org/donate, and we thank you so much for your contributions. You can also write to info@meer.org to be in touch. Now, let me tell you about our guest speaker. Dr. George Tselioudis is a research scientist at NASA's Goddard Institute for Space Studies. He analyzes satellite observations and model simulations to understand the interactions between the Earth's atmospheric dynamics and thermodynamics and the components of the energy and water cycles, and quantify the resulting feedbacks on climate change. If anyone has questions that come up while George is presenting, please send them to co-host Barbara in the chat. Okay, George, we are eager to hear what you have to say, so please take it away.
Thank you very much for inviting me. I had the opportunity to learn a little bit about your organization, and I think that it's a great idea, and it's doing great work in a very careful manner, from what I understand, by trying to always consult with the local communities for any solutions that you're proposing, which I find to be a great thing to do. So I'm really happy to speak to an audience that's related to MEER. And of course, I will be speaking about the Earth's radiative balance, which is basically central to the methods that you're using in your organization. So what I will be talking about, of course, will be at a much more of a global scale. However, overall, it's several similar concepts related to the absorbed solar radiation at the surface of the Earth and how that changes. So I wanted to start by doing an introduction to what we call the Earth's general circulation, or the general circulation of the Earth's atmosphere, more correctly, because it will help us to understand the points that I'm trying to make later on in the talk. So basically, the Earth, if we look at it on a planetary scale, has those circulation cells that you see on the left of the screen, on the left of the globe, and those circulation cells in the tropics, they're called the Hadley cells. There's the northern hemisphere and the southern hemisphere Hadley cells. Then there's the mid-latitude cells in the two mid-latitude regions, and then there's the polar cells in the polar regions. Now, how are those cells formed? Basically, the reason for the formation of the cells is that, first of all, the Earth is round. That's one big reason for it. And being round, it receives a lot more radiation in the tropics than it receives at high latitudes. So once the radiation is received in the tropics warm, and then the tropics export that heat towards the high latitudes. Now, the other reason that the circulation looks like it is that the Earth is revolving around its axis. So a force that we call Coriolis force is introduced that turns the circulation into a specific direction in each hemisphere. So basically, what happens in the tropics? So let's start with the tropics to try and explain this circulation. What happens in the tropics is a lot of heat is coming in. That heat produces a lot of evaporation at the surface that lifts the air uh, near the equator to higher levels. And once the air reaches the top of the troposphere, it starts spreading towards the high latitudes. So if you see those Hadley cells, the two Hadley cells in the two hemispheres, they have a branch where they're going upwards in the tropics, and then the air is moving towards the polar regions in both hemispheres, south in the southern hemisphere, north in the northern hemisphere. Now, in the region where the Earth is going upwards near the equator, we have a lot of ascending motion. Now, ascending motion always produces clouds because it takes the humidity from the surface and brings it to higher levels. So this is the region near the equator, which we call the ITCZ, the Intertropical Convergence Zone. There's a lot of convergence in the surface, which lifts the air up and makes these storm clouds right near the equator. And you can see those storm clouds in the Atlantic Ocean in that satellite picture that I'm showing. I try to circle the ITCZ in the Atlantic Ocean in that plot. So so here's the first storm area that we're interested in the tropics. The ITCZ is one storm area in the tropics that produces a lot of high, very thick clouds that rain a lot and lift the heat from the surface towards the upper troposphere. Now, as the air is moving poleward in the two hemispheres, what happens in the subtropics, the area that's between the tropics and say 30 degrees north or 30 degrees south, is there's a lot of subsidence. So the air that goes up in the tropics comes down in the subtropics. Now, when there's subsidence, then there's cloud clearing. We don't have too many clouds in the subsidence areas. We have low clouds that form because there's still humidity at the surface, but we don't have many clouds in those subsidence regions. So if you see those areas between 0 and 30 south and 0 and 30 north, which is the subtropical regions, in these regions, we have fewer clouds. We have clearing, let's put it this way. We have low cloud cover. Now, once the air reaches about 30 north, from there on, the Coriolis force turns the air to the right in the northern hemisphere, to the left in the southern hemisphere, well, to the right as we see, to the left as the air sees itself, and it creates those jets, the mid-latitude jets, the northern hemisphere and the southern hemisphere. Now, in these jets, what's created is what we call the mid-latitude storms. The mid-latitude storms are the areas where it's those comma-shaped areas that we see in the news when we're looking for the weather. Those comma-shaped areas have high clouds, the high thick clouds. They have also rain. They're the main rain producers in the mid-latitude areas. So these are the regions in the mid-latitudes where a lot of clouds are produced. So if we look at this picture now, so basically, if I start at 60 north, I have the mid-latitude storm regions between, say, 60 north and 30 north, very cloudy area. So that's my one storm region number one, the northern hemisphere mid-latitude storms. Then I go to the subtropics, and in the subtropics now, I have a clearing area. It's not clearing because there is still low clouds, but clouds are a lot fewer. There's a much lower cloud cover in that area. Then I come to the tropics, and then I have a very thin area of, again, very thick clouds, which is the ITCZ. Then come the southern subtropics, where I have another clearing area, the southern subtropical area, where I have low cloud cover with mostly low clouds. And then I have the mid-latitude storms of the southern hemisphere. And there again, I have thick clouds with a great cloud cover. So this is from a just an instantaneous picture. So if I take the clouds over a whole year and make an average of the cloud cover, what do I come up with? I come up with a very cloudy storm zone in the northern mid latitudes, and then a much lower cloud cover zone in the northern subtropics. Again, a very high cloud cover zone in the ITCZ, another low cloud cover zone in the southern subtropics, and then another storm cloud zone in the southern mid latitudes. Well, if we go to the next slide, you're gonna see on what you see here now is the cloud zones uh, yearly, the annual average of the cloud zones as they're changing from 1983 until 2020. 2021, I think it's in this plot. So basically, what do we see here? First of all, let me explain that this is total cloud cover that you're seeing on these plots. So red means a lot of clouds, blue means low cloud cover. So what we have here, we have the northern mid-latitude zone, but between 60 and about 35 degrees north, very high cloud cover, the red zone. Then we have the subtropical zone, low cloud cover, that's the blue zone. Then we have the ITCZ, the thin zone near the equator, that's red again. Then we have again the subtropical zone in the southern hemisphere, the blue one, which again it's low cloud cover. And then we have the southern hemisphere mid-latitude storm zone, where again we have a very high cloud cover. Okay, so basically this is the annual mean picture for the Pacific and the Atlantic. And these are what we call Hofmuller plots, which are showing you how those zones are changing through the satellite era from 1983 until almost the present, let's say about 2021. Now, what do we see on these plots? If I go to uh, the thing that really stands out is that the blue zones, remember the blue zones are the zones with a very low cloud cover, are expanding in both directions. As time passes by and we go from left to right, those blue zones are expanding and they're becoming larger and they cover more and more latitudes. Now, this expansion of these low cloud cover zones has two effects. First of all, it pushes towards the poles the storm cloud zones, both in the northern and in the southern hemisphere. And it also squeezes, basically, it narrows the ITCZ. It makes it a lot smaller. So this was a result that we published in the paper last July came out, where we're saying that the what we see when we look at the satellite data from 1983 on, what we see is an expansion of the low cloud cover zones in the northern and the southern hemisphere, a contraction of the storm cloud zones in both the northern and the southern hemisphere, and a narrowing of the ITCZ. Okay, so these are the main results that we find when we examine the satellite record of the last 42 years. So we've extended this plot to 2023, and the result is very similar. I'm just using a slightly older plot here, but nothing changes when we extend it to almost the present. So basically, these were the main conclusions of this paper that we published back in July. But now the question is, well, what is the effect of this change to the radiation? Because you understand that if you're expanding the zones that have low cloud cover, you're letting more sunlight in. And if you're contracting the zones that have large cloud cover, like the storm zones in the two hemispheres and the ITCZ, again, you're letting more sunlight in because of this. So this is what we try to look at the next paper. So we go to the next slide. Uh, oh, okay. This is I'm trying to. I showed one record, which shows the changes from 1983 until the present. Uh, Now, this record is a patchwork of many satellites, so it has some uncertainties to it. So people always see it with a little bit of skepticism. So I redid this with our best available instrument, which is the MODIS instrument, but only starts in 2000. So I did this with the MODIS instrument on the left between 2000 and 2025, and the same result shows. Not as impressive because the more data you have, the clearer the trends become, but it's in the same direction. And now, along with the MODIS, we have the Cirrus product, which is basically showing you what happens to the reflection zones of so the left is clouds, the right is reflection. So red is a lot of reflection, blue is less reflection. And again, the area of smaller reflection is expanding, the area of larger reflection is contracting over the last 25 years. Okay, so let's go to the next slide. I think you need to hit again. Yeah, okay. So basically, if we look at those cloud zones on a map, this is a little bit how they look like. So you see the white on top is high cloud cover, the blue is low cloud cover. So you can see the southern hemisphere storm zone, which extends between 65 south and 35 south all the way across the Southern Ocean, which is the high cloud cover zone, the mid-latitude uh, high cloud cover zone. We see the ITCZ in the tropics near the equator, which is the high cloud cover zone in the equator. And then we see the two storm tracks, one in the Pacific and one in the Atlantic in the Northern Hemisphere. Now, the bottom one now is not clouds now, it's reflection. Again, red means a lot of reflection. Green means much less reflection of clouds, so much more sunlight coming in. Very little sunlight coming in when it's red. A lot more sunlight coming in when it's green or blue. And again, it's the same regions. The two storm tracks in the Pacific and the Atlantic, the Southern Ocean storm track and the ITCZ. Now, the question is, what happens to those regions over the last 25 years that we have very good observations? So what we did is we took basically the area coverage of those regions and we plotted the trend in the area coverage of those regions. So if you hit return, yeah. So these are the three regions on top for the clouds. The yellow one or orange one is the Southern Ocean. The green one is the ITCZ, and the blue one is the Northern Hemisphere storm track. And you see that those regions are contracting. The intense storm regions with the very reflective clouds are contracting, and at the bottom is the high reflection regions, which pretty much coincide with the high cloud cover regions because the reflection is coming primarily from the clouds. So you can see that the high reflection regions, the storminess regions, which reflect a lot of sunlight, are contracting both in the northern hemisphere, in the southern hemisphere, as well as in the tropics. So this contraction um, of course, is going to let more sunlight in. I mean, it's easy to conclude that more sunlight is going to come in because those areas of stronger reflection of sunlight are contracting. And of course, this is what we see. In the last 25 years, there has been a lot of discussion of the fact that we see a lot more sunlight reaching the surface. The absorbed shortwave radiation has been increasing in the last 25 years, and we're trying to understand why. We have, if we hit what return once more, uh, this is the absorbed shortwave radiation. The black line is for the whole globe, and then the other lines are same as in the previous plots for the northern southern hemisphere and the tropics. And there's a lot more sunlight coming in to the tune of about 0.45 watts per meter square per decade. More sunlight coming in, and the question is why. So a lot of suggestions have been made in the scientific community, which are all valid and but with those suggestions, we couldn't explain 0.45 watts per meter squared increase in absorbed sunlight, absorbed solar radiation. One explanation is the decrease in the aerosols. There has been a large decrease in aerosols, which started back in around 2005 or so, 2002, 2003. Especially in China, there was a big reduction in aerosol emissions because they needed to face the problems with pollution in their big cities. Plus, they were organizing the Olympic Games in 2008, and they needed to clean up the air in Beijing and all that. So there were a lot of measures taken in China to reduce the aerosols. Now, reducing the aerosols is what Jim Hansen, who was the old director of our institute, and I work with him even to this day on several different papers. He calls it a Faustian bargain because when we emit greenhouse gases, which of course warm the atmosphere, at the same time we emit aerosols, which cool the atmosphere. So the net effect is a balance between the aerosols and the greenhouse gases. However, we knew from the beginning that if at some point we would need to reduce the aerosols because the greenhouse gases, no matter how big of a negative effect they have on the Earth's temperature, are not uh, directly affecting our health. The aerosols do directly affect our health. Pollution is one of the main killers of our present time. So we knew that we would need to reduce aerosols at some point, and of course we started doing that. And the moment we're doing that, well, we're letting more sunlight in from the aerosol effect. And also in 2015, there was an agreement that had to do with shipping, the emission of aerosols from shipping, that there be reductions, which started in 2015 and became even more strict in 2020. So there were more emission reductions in aerosols because of the shipping aerosol reductions. So all those things are reasons for why we would expect to see more sunlight absorbed at the surface of the Earth. However, if when we put all those things together, we cannot come with zero point 0.4 watts per meter squared. We can per decade. We can come maybe with 1.1, 1.5 watt per meter squared, 1.7 watts per meter squared at best. But we cannot come with 0.45 watts per meter squared with all those other reductions. So what we're suggesting here is that the additional amount, in addition to the issues with the reduction of aerosols and all that, an additional amount of increased absorption of solar radiation comes from the fact that those zones are shrinking. The storm cloud zones are shrinking both in the northern and southern hemisphere and in the tropics. and is letting more sunlight in. So if we go to the next slide, and this is, I'm not gonna go into the calculations here, but this is how we try to see how much of the change of the 0.45 watts per meter squared can be explained by the contraction of the storm cloud zones, and we find that it can be up to 0.37 watts per meter squared that can be attributed to the narrowing of the cloud zones. Uh, so it's a fairly large effect, and it's happening in the record of the last 23 years. There is uncertainties to it, but we're fairly confident that our estimate has of course an uncertainty of probably about uh, 0.05 or 0.07 watts per meter squared, but we're pretty confident that it is a correct estimate. So if I can have, I think, the last slide. So the last slide, I don't know, those of you who are old enough remember that Saturday Night Live, there was a session that was called Deep Thoughts by Jack Handy. He would come up and say the most profound things in a very deep and serious voice, and they would all sound very serious, even though they could be very trivial observations. So when I was writing this, I mean, I was saying things that I don't know if they're trivial or not, but it sounded to me like I was doing deep thoughts. So basically, this is saying that this contraction of the storm cloud zones can have an effect of up to 0.35 watts per meter squared additional uh, absorption of sunlight. So this is really serious. The other thing that the other thing that is the bigger question, of course, is, okay, is this caused by global warming, and is this going to continue, or is this some sort of natural variability and it's going to stop? And this is the main question here that we're faced with. And to be honest, I don't have the answer. I'm not 100% sure. There are several reasons why this could be related to global warming, and it will continue in the future. I showed you those cells. Uh, the question is, why would the Hadley cell be expanding more towards the poles in both hemispheres? Is that because of global warming? Well, it can well be because of global warming, because global warming is changing the temperature gradient between the poles and the low latitudes, and that temperature gradient is the driver of the circulation. So if we change that temperature gradient, we change the driver, we change the battery basically of the circulation. So that can cause the expansion of the dry zones, of the low cloud cover zones poleward. But again, this is something that we need to study a lot more closely. We need to be a lot more certain. So this is what the next phase of my work is. I'm trying to understand why this expansion is happening, and see whether it will continue in the future and what kind of an effect it will continue to have. Okay, I think I'm going to stop here.
I would like to please remind the audience that we will soon be taking questions from the audience, and you can send them to Barbara, co-host in the chat. But first, we're going to bring on some members of the MEER community. So I would like to first welcome Paul Beckwith. And you met Paul's cute dog, and Paul is a well-known climate system science educator, joining the dots on abrupt climate change. He's an occasional part-time professor of geography, climatology, oceanography, and environmental issues at the University of Ottawa. He has a bachelor's of engineering physics and a master's degree in laser optics, and he was awarded the Association of Professional Engineers of Ontario Gold Medal. Welcome, and thank you for joining us, Paul.
Well, thank you for having me. So, a couple quick questions right off the bat. George, thank you very much. Very fascinating stuff. I'm glad to hear that you're actually working with James Hansen. So, you're well aware of his views on the sulfur and so on. I mean, if it is the sulfur that's a big component, then of course there's going to be a big asymmetry between the northern hemisphere and the southern hemisphere, right?
Yeah.
So maybe you can comment a bit more on your data because it looks like the effects of are happening in both hemispheres, and also it would also make an asymmetry between the Pacific and the Atlantic, which I'm not sure if you're seeing in your data. And another big question is, have you communicated with Jennifer Francis, who I would say is the leading expert on polar amplification, causing a waviness of the jet streams because of the reduction of the temperature gradient, which you talked about.
Mhm.
So those are a couple quick questions for you.
Great. Yes, very, very insightful questions. First of all, yeah, I've been working with Jim in a couple of papers lately. We had a paper 3 years ago, and then we had another one, the global warming in the pipeline, that came out recently. I'm a co-author on both of those papers. There's no question that the aerosols, sulfate aerosols, are a part of the solution. Um, the the asymmetry of the two hemispheres is true, and it's something that is working against that explanation. However, if you look at maps, the bullseyes of the increased solar absorption are the North Pacific and the North Atlantic. That's where most of the absorbed solar radiation, the increase in the absorbed solar radiation, is occurring. So then, and these are also happen to be the areas of the most intense shipping routes. But things are happening in the Southern Ocean as well, and the shipping routes there are not as are certainly not as frequent. But even in this last paper, that we did with Jim, our best estimate, which is at the very high end of the estimates, are that the aerosol effect can be of the order of uh, um, at point 1, 1.4, 0.15 at best. 0.17, I think, is the upper limit that we have there. But we're talking about a change of 0.45, so there's still a lot of room left. And it is recognized that it's the cloud feedback, that it's the contributor to the rest of the missing piece. The question is what kind of a cloud feedback? A lot of the discussion was that it's cloud feedback related to microphysical processes, and it may well be a part of it. The decrease in the subtropical zones can be coming from that, but we're proposing another solution, which is dynamically driven, which seems to be contributing significantly. So that, as far as the aerosols go. Now, I haven't talked to Jennifer Francis lately about my results. We didn't run into each other in any meetings, but I've talked to her in the past, and her work on the effect of the change in the meridional temperature gradient has to do with the fact that weaker meridional temperature gradient produces more of a wavy jet stream, which produces more of the extremes. It can even produce extreme cold spells as well, of course, as extreme heat waves because of the decrease in the amount of eddy kinetic energy in the jet, which makes the jet a lot wavier than a stronger jet. But what I see, and some other people see, and I don't remember if Jennifer has looked at that in detail, is also a shifting of the jet stream poleward in both hemispheres, and so in addition to the increase in the waviness, a shifting of the jet stream poleward, which I mean the two are not independent of each other, of course.
Yeah. Quick follow up, and then I'll let other people step in. The Have you looked at the ENSO effect? We know with an El Nino there's warming 0.2, 0.3, and with the La Nina cooling. Could some of that effect be due to a change in the cloud, in the nature of the clouds during those phenomena? That's the first question. Second question is the AMOC. We know it's slowing down. So there's certain areas in the North Pacific that are cooler. Are we seeing a difference in the clouds associated with an AMOC slowing down? And the third thing is, can you give James a kick in the butt and to get his book finished?
Well, we're trying to do that. He's been he keeps adding more and more things. As things keep coming up, he says, "Well, yeah, but now I have to include this as well." And I keep telling him that, well, this is never gonna end. There's
Right.
always gonna be new things coming up. So you got to at some point say that this is where I'm stopping, and I'm just gonna include and forget what happens and just put it out there. But yeah, no, this is a saga that's been going on for a long time now. So in terms of
The
the other
ENSO.
questions, the
Yeah.
ENSO, yeah, the ENSO is definitely affecting the clouds, and it's definitely affecting the storm tracks, because the ENSO creates a pattern which is a southern oscillation, which creates high and low pressure, permanent high and low pressure centers over mostly the North American continent, and affects the jet stream. However, I mean, we have a record now of about 24 years, which includes both strong ENSOs, La Niñas and El Niños and La Niñas. And these trends are there even if we remove the ENSO signals from them.
Okay.
So the ENSO plays a role, but it's not the causal role for these changes. And as for AMOC, yeah, AMOC is certainly affecting the North Atlantic storm track. We have this warming hole in the North Atlantic, south of Greenland, which we try to understand, and it doesn't seem to be driven by the atmosphere. It seems to be driven more by the ocean. So that complicates the picture in the North Atlantic storm tracks a little
Right.
more.
It also
Uh,
increases asymmetry between the Pacific and the Atlantic,
yes,
I would
yes,
say, in your data. Yeah. And also
that
between the northern
that
and southern hemisphere,
that as
because
well. Yes.
ENSO's primarily a northern hemisphere Atlantic basin phenomena. But anyway, yeah, thank you. I'm sure there's lots of other questions, so I'll mute myself. Great talk.
Thanks.
Thank you.
Thanks for the nice questions.
Yes, thank you so much, Paul. And I would like to now welcome and introduce Herb Simmons, another member of our MEER community, to ask questions. Herb Simmons is a longtime climate leader. He has co-founded 3 climate action groups and is the author of A Climate Vocabulary of the Future, which has been called a science poem and a prophecy by the noted author Kim Stanley Robinson. Herb serves on the steering circle of the Healthy Planet Action Coalition, an international group committed to restoring a safe and healthy climate. Additionally, he is a board member and serves as an event moderator for the Climate Emergency Forum. Welcome and thank you, Herb.
Oh, thank you, Kathy, and thank you so much, George. That was really obviously a very rigorous, well done, and extremely important piece of work in a series of work that you and your colleagues have been doing. So my own background, as was sort of suggested, I don't have a scientific background, and most of the work I've done in my life and in my work now, I try to put myself in a position of sort of translating scientific and other evidence into policy. What are we going to do with this information? Is it research? Is it action? If it is action, what is the action needed? Who can do it? How quickly? And on and on. And obviously, we have neither the time to get into great detail, and I recognize and respect your role as a scientist, whose primary, you can correct me, whose primary mission is to generate knowledge for the rest of us to evaluate and act on. But you yourself said you worked with and have in a very close relationship with Jim. I had the same question as Paul. When is his book coming out? So you began to provide a bit of an answer for that.
Sure.
And and Jim, as you know, and some people here may or may not know, I think he actually coined the term scientific reticence years ago about the role of scientists basically sort of not being out there promoting action or whatever, but we're not studying 9th century Tibetan art.
Yeah.
We're studying events and phenomena that will affect the lives of every person on the planet and most every other creature. So with that, and of course, Jim has come out for, and I've heard him say it in various forms and in writing, some form of at least accelerated research, if not deployment, of solar radiation management at this time. So I guess if you were asked to be an advisor to a policymaker, let's say at the international level, um, and that person said to you, based on everything you know and everything you have discovered so far, what advice would you give us to minimize the risk of the climate crisis getting out of humanity's control?
Well, my answer now would be different than my answer about 4 or 5 years ago. The the changes that we see in the past 5 years have been very much on the high end of our projections. This is why we're struggling to understand why this is happening. We're trying to understand why this solar absorption has been increasing so much so fast in the so 5 years ago, my advice would be for a more measured and slower approach towards cutting down emissions, of course, which is the uh, basically it's the only viable solution at this point in time. But now the advice would be that not only we need to be reducing emissions with much higher urgency than we had before, and we seem to be doing the exact opposite, by the way. Uh, but we also need to start addressing issues of geoengineering and start addressing possible ways of interfering with the system, which I wouldn't want to even suggested, like I said 5 years ago, because I understand how complicated the system is and how naive you can be by thinking that doing something is going to have a very direct cause and effect, but in a very complicated nonlinear system, this never the case. However, now for the first time, I would I would suggest that those solutions need to be explored with the mindset that then we may have to apply them in the very near future, within the next 5 or 10 years.
If I could, in the groups that I've been involved with recently, the advocacy groups, I have been, and I think my colleagues have been, kind of frustrated because we found it very difficult to find either in the activist community or in the scientific community or in the policy community people willing to say what you have just said, that essentially based upon the empirical evidence of what you are discovering and what we are seeing, not just in terms of your study here, but in a whole bunch of other areas where the crisis has accelerated. So I think I just want to thank you and tell you how much I appreciate that, because it's not easy necessarily to shift to a position that we all know is extremely controversial, that may not be welcomed by sectors of our society, is not welcomed right now. And so again, I don't have any follow-up questions except to say I really appreciate that you've come out so clearly stating that we're in a different world today than we were 5 years ago, and we've got to broaden our perspective. In my group, what we talk about is the climate triad, that we need to accelerate emission reductions, as you said. We need to explore how we can pull down CO2 and other greenhouse gases, if feasible, as quickly as we can. And we need to directly cool the climate to buy us the time and the space to be able to do the other things that you're talking about. So thank you very much, George. Really appreciate your work.
Welcome.
Yes.
Thank you.
Thank you. Thank you, Herb. Thank you, George. George, one more. I wanted to just kind of introduce and call out one other person from our community, and that is Mike McCracken. He couldn't be here today, but he kindly shared some questions with us in advance, and I'll just introduce him and then choose one of them so that others have a chance to ask questions. So Mike McCracken, the first half of his career mainly involved modeling the climatic effects of natural and human activities at the Lawrence Livermore National Laboratory. During the second half, he served as senior scientist at the Interagency Office of the U.S. Global Change Research Program, and then, among other activities in retirement, as chief scientist for climate change programs at the Climate Institute, with a stint as president of the International Association of Meteorology and Atmospheric Sciences. And so one of the questions that Mike asks is, given the reduction in clouds, well, due to the many factors you mentioned, but also due to reduced freighter emissions, what does that tell us about how much cloud condensation nuclei would have to be created for marine cloud brightening to have a large-scale influence?
Well, it's hard to give a quantitative answer. My thinking is that qualitatively, there are some things we may be able to do. For example, you never want to reverse clean air measures like the reduction of sulfate pollution from ships, but it may be the case that we can allow it to happen mid-ocean, but not near ports, which would help in a way with cloud forming and cloud brightening as well, if we do that. So that could be a measure that can be taken or reversed in a sense. But I mean, quantitatively, it's hard to give an answer. We're going to need to run some modeling tests with models that we trust their cloud formation schemes in order to see how much of an effect that would have. But measures like that, for example, I'm assuming that we can take easily and I think they could help.
Thank you. Thank you very much. And I will now move to some questions from our audience members who are here. This question comes from Martin. Here in the spring in the Northern Hemisphere, we can observe a phenomenon called Earth shine, where the dark part of the moon is slightly lit up by light reflected by Earth. This is sometimes described as the new moon holding the old moon in its arms. It is fair to assume that enhancing the albedo effect of the Earth, creating more reflection, would cool down. Is it fair to assume that enhancing the albedo effect of the Earth or creating more reflection would cool down the Earth?
Yes, most definitely, yes. There has been some research. I mean, there are people who have data sets related to the moon reflection of Earthshine, and I haven't seen any lately to see if somebody tried to look at the changes of the past 5, 10, or 10 years using data sets like that. I'm surprised that somebody hasn't come up with a paper, but I haven't seen one, or maybe it escaped me, but I probably would have seen it if it came out. But yes, most definitely, an increase in reflection is definitely going to cool the planet. The question is, how do we increase the reflection? There's several ideas. One is increasing the cloud condensation nuclei in order to make more and brighter low clouds over the oceans. There are other ideas of injecting aerosols in the stratosphere where they stay longer and can have a cooling effect for longer periods of time. Those are all, like I said, geoengineering ideas, which, as I said in the preceding discussion, I wasn't really in favor of 5 years ago, but I'm definitely seeing that they may become inevitable in the near future.
Right. Thank you. We have a couple questions from Gregory. Is the implication here that for any solar radiation management project which has the goal of global scale cooling, the best place to try and raise the albedo would be in the low total cloud cover regions? And then second to that, should we expect increases in desertification to be concentrated in the low total cloud cover regions?
No, I mean, the increasing the reflectivity of the low clouds is easier than increasing the reflectivity of the high clouds. So because you can reach them easier, but any increase in the solar reflection can be done in any region. I mean, you can do it at the surface, like the the projects that you guys are doing, or you can do it in the stratosphere. It doesn't for cloud brightening. The low clouds are the easiest target because the high clouds are a little. If they're thin, they're more warming than cooling. So you don't want to increase the high thin cirrus clouds because those are warming elements because they block more solar radiation, more thermal radiation than they reflect solar radiation. So you definitely don't want to increase the cirrus clouds, the thin cirrus. So the low clouds are the more logical target, both because they're easier to get to and because they're purely they make very little difference to the thermal radiation part of the budget, and they certainly increase the reflection in the solar part.
Thank you, George. I think I may have misemphasized the low part. I think that I'm thinking that what Gregory is referring to is in your models, would it be more effective to target the areas that have such little cloud cover? Not necessarily low or high clouds atmospherically, but just the regions that were shown on your model, on your maps that have so little cloud cover. Would those be, if we're looking for global scale cooling, should we try and raise the albedo over those areas that were mostly blue in the graphs, the very low, the areas of very low cloud?
Yeah, those are the areas that you can target the most. It has to be, I mean, it's a little bit of a bargain, because you need to have some humidity available to make the cloud uh, to start with. So you cannot target areas that are extremely dry, because no matter how much condensation nuclei you have, you're not going to make clouds if there's no available humidity. So that's why we're concentrating in ocean regions where you have surface humidity. But yeah, those are the regions to target, because the regions that already have high cloud cover are more or less saturated in the reflection part. They reflect as much as they as it's possible in those regions. So the blue regions, yeah, the low cloud cover regions are the regions that we will target for cloud modification and increase in cloud reflectance.
Great, thank you. We have a question from Jeff. Will aggressive surface sunlight reflection on land between 0 and 30 degrees latitude also enhance ocean clouds in the Hadley cell zones?
Enhanced reflection of sunlight, whether it will enhance cloud formation?
Yeah, enhanced sunlight reflection on land.
Yeah,
Will that also help enhance ocean clouds?
probably not. If we reflect more sunlight over land, it means that we absorb less sunlight at the surface, or we warm the surface less, and that reduces evaporation, uh, and we need the evaporation to form the water vapor in the atmosphere that makes clouds. So I haven't thought of that in detail, but my original thinking is that if we enhance surface reflectance over land, we're we're definitely, I don't see any way that would enhance cloud formation over ocean.
Okay, thank you so much.
Mm-hmm.
And I think that we will take this opportunity to come to a close. And George, I want to thank you again so much for coming to MEERTALK today, for furthering our climate education. The complex interactions and feedbacks that you discussed today are deeply distressing to me, yet vital to understand to help us make wise decisions and advocate for appropriate action. So we are really thankful that you joined us today.
Well, thank you for inviting me. And like I said at the beginning, I think that you're doing a great job with your organization, and I'm glad that I could help a little bit.
Thank you. Thank you very much. You help a lot.
Thank you.
At MEER, we are working to help educate the public while also developing technologies to help curb the warming on the planet. We invite you to keep learning about Earth's energy imbalance and climate science on our website. We are a primarily volunteer staff, so please consider making a monthly donation of any amount if you have enjoyed being here today or watching our MEER Talks on YouTube channel. Also, please check us out on social media. And if you found being here beneficial today, please tell someone else about MEERTALK. We hope to see you all again for our May 4th MEERTALK, when Dr. Thomas Romge will present. So thank you very much for coming, and enjoy your week.